But this is an earlier final exam, and I'm using that as a review. So let me go down to 50. That's the one that stumped me, but I was on the right track. For some reason, I got confused. I think it was 50. Yeah, there it is. Yeah. Okay. So let me be sure we hadn't had new visitors. Yep. Anne's here. I believe I got everybody else. Okay. All right, I'm going to balance this equation. And this is number 50. So we got potassium iodide and nitric acid. Oops. Yields. Potassium nitrate. And NO. And I2. And H2O. All right, so if you recognize an equation that is a redox equation, and this one's already got water in it. Now we could split it up like we do for the half reactions, but sometimes if you start off with what's my word for it? The line trace version, and identify the reduced and the oxidized components, then you can balance the electrons first and follow that up with the budget method. All right, so this is potassium's going to be the same on both sides. Iodine's -1. That's +1. This is -2. So that's -6, and +1 is -5. So this has to be +5. This is also going to be +5 because there's a nitrate, there's a nitrate. Same thing. Only this nitrogen is a +2. That's a 0, -2, and +1. Okay, so which one is oxidized and which one's reduced? This iodine went from a -1 to a 0. That means it had to lose an electron. So we have a loss of 1 electron for each iodine, but we have 2 iodines. So we're going to need 2 iodines on this side to balance those electrons. Okay? All right. Now, which one was reduced? Well, nitrogen went from here to there. It also went here, but it went to there for the reduction step. And this is a gain of 3 electrons per nitrogen. Okay? We can, let's see. Let's go ahead and balance that part, 2 potassiums. We're going to have to leave this coefficient out because we've got nitrogen occurring in both places. We're going to fix that in just a minute. But this is 3 electrons per nitrogen, and we only got 1 nitrogen, which is 3 electrons. Now, what we need to do before we go any further is balance the electrons. So if we've got 3 electrons in this reduction and 2 electrons in the oxidation, we need to cross multiply them. So how do we do that? Well, we need 2 times this one to give us 6 electrons. So we need 2 here and 2 here, right? And we need times 3 for this one, 6 electrons, times 3 for this one. So 3 times this one is going to be 6 and 6. Oops, sorry. No, that's right. 6 iodines. No, this only needs to be 3. One electron per iodine times 2, and then times 3 gives you 6. Yeah, that's right. Okay, now that we have the electrons balanced, we can go to the budget method. I'm going to clean this up. That's a 6. And let's clean these up a little bit too. Okay, now we can do budget method. So since nitrogen splits out of this one into 2 different places, we have to account for every element. So potassium, iodine, hydrogen, nitrogen, and oxygen. Now we got 6 potassium here. We got 6 iodine, got 2 hydrogens. We've got 2 nitrogens, and we've got 6 oxygens. Now, let's see, that's 12, 13, 14, 15, 16, and 6 is 22. So it should be 22. 18, 20, 22. That's right. Okay, on this side, we got 2 potassium. We've got 2, 4 nitrogens here. We've got 6, 7, 8, 9 oxygens. And we have 6 iodines. And hydrogens. We have 2 hydrogens. There we go. Now we should have, let's see, 13, 14, 15, 16, 17, 23. Let's see if we got 23. 2, 4, 6 is 10, 12, 14, and 6 is 20, 21, 22, 23. Okay. So we've done the initial tally correctly. Now, we're going to hold iodine out till the last, because when we change the coefficient for iodine, if we need to change that one, then it only changes iodine. So let's look at potassium. Right? We need 6 potassium, and potassium only occurs in one place. So let's change this to 6. That makes 6 potassium. Now that changes nitrogens. 6, 7, 8, 8 nitrogens. Okay. And it also changes oxygens. 18, 19, 20, 21. Okay. Let's see. Let's fix the, well, we can't actually fix the oxygens yet. Let's do the nitrogens. So we need 8 nitrogens on this side. That means this has to be 8. That also gives us 8 hydrogens. Right? And it gives us 24 oxygens. Okay. Let's see. So now we're down to hydrogens and oxygens. So what if we fix the hydrogens and see if it fixes the oxygens? So 8 hydrogens on this side. It only occurs in one place. So a 4 here will give us 8 hydrogens. And it'll change 4 oxygens, 5, 6, 6, and 18 is 24. We're balanced. I know that's a lot of work, but it shows you how to combine the tie line method with the budget method. Okay, that takes care of 50. Now, the one that was giving us trouble was, I think 51 gave us trouble. Yes, I remember 51 did give us trouble. Okay, here's the problem. Remember, we thought we had oxygens left over? That's because one of these equations was written incorrectly. And it should be, let's see. Let me get my picture. The other direction. It was acetylene and oxygen. It's this one right here. So let me fix that. Well, I may not be able to fix it because of the way this thing is built. But that one right there, this oxygen should be 5 halves, not 1 half. If that's 5 halves, then it comes down here to the one with acetylene. This is 5 halves. And that 5 halves will cancel both this 1 half and this 4 halves. Okay, so it will balance out and you get the right number, minus 713 kilojoules. All right. Now let me see if I can figure out where we left off. Unless somebody wants to tell me where we left off. I think we did that one. We did this one. We did that one. I don't know if I marked it. We were into the bonuses, weren't we? Yeah, we did those. Did those. Here we go. This is where we got to. Stretch that back over here. Okay, so we're going to pick it up with 63. All right, I'm going to read from I got stuff in my way here, so I'm going to read from the screen. 3 samples of a solid substance composed of element A and Z were prepared. The first, okay, so we've got 3 preparations. Of a compound. The first one is 4.31 grams of A, is analysis of the compound, 4.31 grams of A, and 7.70 of Z. Okay. The second preparation is 35.9% A, And that should be by mass. And 64.1% Z. Okay, and the last one is 0.718 grams of A reacted with 2 grams. Let's see, 0.178 grams of A, 781, excuse me, dyslexia. A. Let's see, how is it worded? Reacted with Z to form 2 grams of the third sample. So 2 grams is total. All right. Yes. Okay, so what you're directed to do is show that these data illustrate the law of definite proportions. The law of definite proportions, if you don't remember, says that any compound, no matter what its origin, its pathway, however you get to that compound, will always have the same mass ratio of elements in the compound. So this tells you the mass ratio right here. So you don't have to do anything with this one. What you have to do is calculate the mass ratio or percentages for this one and that one. And this one is going to be divided by the total mass. Well, actually, you can do it a number of ways. If we're going to stick to the, if we're going to stick to the law of definite proportions, we should do a ratio. So the ratio then would be 4.31 ratio to 7.70. Let's see. Well, this is okay. I did a little bit different in the explanation there, but this will also work. This gives it the ratio of A to Z is 0.5597. If you take the reciprocal of that, you'll get the value that's right there on the screen. This is A to Z. Okay. This one, all we have to do here is ratio that percentage to that percentage. Because if they're based on 100 grams each, then you can say this many grams to that many grams. So 35.9 divided by 64.1 is equal to 0.56006 A to Z. Close. How about this ratio? That's the total. So what's the Z amount? The Z amount is this one minus 0.718. Which is 1.282. Now we can do the ratio of A to Z. This is, that's right. 0.718 divided by 1.282. And that's 0.56006 A to Z. Okay. So within experimental error, these values are the same. And that demonstrates the law of definite proportions. The mass ratio of A to Z is the same in each one. As demonstrated here, it's the ratio of Z to A. 6 of one, half a dozen of the other. You still have the same proportion. All right. I'm not sure if we're going to have enough. I'm going to try to finish. I don't think I've selected any. No, we should have enough time. This should be okay. If not, then I'll just stick around and finish the video. 63. Excuse me. 64. In a metallurgical process, the mineral pyrite. This is pyrite. Right? What else does it go by? What other name? Fool's gold. This mineral looks like gold as far as its color goes, but it has an entirely different structure. It's a crystalline structure, whereas gold is a metal. Okay, anyway, if we roast it in air, that is, we combine it with oxygen, what do we get? We get Fe2O3, rust, plus SO2. Okay. The SO2 is then converted into sulfuric acid in the following reaction. Okay. Assume the mineral is 24% FeS2, and the remainder is inert. So this mineral is only 24% FeS2. This is the mineral. We're assuming purity here, but the mineral is actually only 24.2% FeS2. The remainder is inert. So what mass of H2SO4 is produced if 155 grams of the mineral is used? Well, 155, look at it this way. All right, let's find out how much actual FeS2 is going into the reaction. That's essential. So 24.2% of 155 grams. So 155 grams of the mineral, and we can do it one of two ways. I just take this decimal, move the decimal and make this a decimal fraction. That's the simplest way to do it. That gives us 37.51 grams of actual FeS2. Okay. So if we 24. Did I make a mistake? Oh, I did make a mistake. It's only 24.0. So this value should be 37.2. Okay. Now, in order to use stoichiometry for any of these, reactions, whether it's a single reaction or multiple reactions, you've got to have moles. Everything is based on moles. So what we have to do is convert this into moles. So we need the molar mass of that compound. Iron is 5585 grams per mole. And 2 times sulfur, 3207, will give us the molar mass of pyrite. Okay, that's 119.99. Okay, divide that into 37.2, and we get 0.310 moles of FeS2. Okay. Now that we got that many moles, if we're going to conduct a reaction in which the sulfur dioxide from the reaction produces sulfuric acid, notice that the ratio here, 2 moles of sulfur dioxide gives you 2 moles of sulfuric acid. So if we find out how many moles of sulfur dioxide are produced in this reaction, that's the same as the number of moles of sulfuric acid, of H2SO4. So what's the ratio here? Well, the ratio is 1 to 1. So that's how many moles, 0.310 moles of sulfur dioxide. And since the ratio of sulfur dioxide to H2SO4 is 2 to 2, or 1 to 1, this is also the number of moles of H2SO4 that are produced. Okay? So now all we need is the molar mass of sulfuric acid, and we can convert that to so many grams. So sulfuric acid, 2 of the hydrogens, the sulfur, which is 3207, and 4 oxygens. So it's 64 for the oxygens, 32.07 for the sulfur, and 2.02 for the hydrogens. That's 9809. Okay, times 0.31. Okay. Oh, wait a minute. All right. Anybody got any idea what I did wrong? This equation is not balanced. Okay. That equation is not balanced. Some of these calculations are still valid, but we're going to have to balance the equation first. Okay, let's see if we can do it without the budget method. 2 irons. Okay, 2 irons. That means 4 sulfurs. 4 sulfurs. So that's 8, 11 oxygens, right? So 4 sulfurs, 2 irons, and 3 plus 8 is 11. 11 oxygens. 11 has. Okay, so if we balance it now, we just multiply by 2, we get 4 here, we get 11 there, we get 2 here, and we get 8 there. Now it's balanced. Okay, we're okay up to this point. This is how many moles of that we started with. How many moles of SO2 do we have? 0.310 moles of FeS2. And then we're going to convert that to, let's see, 4 here and 8 SO2. So that's double that, 0.620 moles of SO2. Now we can do the equivalence. 2 SO2s yield 2 H2SO4s. So 0.620 moles of H2SO4. And now we just convert that and I'm going to have to do the calculation again. 2.02, 64, and sulfur is 3207, 9809. times 0.6. 5 point, no, that's not right. Hold on a second. 0.62 and 98.09 times 60.8. 60.8 gram of H2SO4. There we go. I forgot the first cardinal rule of stoichiometry. Balance your equation. All right. That was 64. $65. All right. 65 requires that you understand what is meant by combustion. C2H5OH is ethanol. C2, yeah, H5OH is ethanol. Combustion requires oxygen. And whenever you combust either a hydrocarbon or an organic compound with oxygen, you can expect to get carbon dioxide and water. That's your starting point. Now to balance it, I'm going to use the budget method. C, H, and O. So we have 2 carbons, we have 6 hydrogens, and we have 3 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and 3 oxygens. Okay, let's do the carbon first. 2, so that makes 4, 5 oxygens. Okay. So let's do hydrogens now. So we have 6 hydrogens, put a 3 here. That gives us 6 hydrogens, and 3 plus 4 is 7. 7 oxygens. Now we can go to the oxygen and make 7. Now, notice here, we've already got 1 oxygen there. So in order to make 7, we only need 6 more. So if we put a 3 here, that gives us 6 plus 1 is 7. And now we're balanced. Okay. All right. Let's see. Toy balloons are filled with hydrogen gas at standard temperature from a 10-liter cylinder. The initial pressure of the gas in the cylinder is exactly 100 atmospheres. Assuming each balloon is filled to a volume of 1 liter at standard pressure, how many balloons could be filled? All right. What we have here is Boyle's law. We're talking the temperature is the constant. The external pressure is at 1 atmosphere, but the internal pressure, the pressure into the balloons is 1 atmosphere. The pressure in the cylinder starts off at 100 atmospheres, right? So if we're going to fill each balloon with 1 liter, so each of our balloons, let's see, 66. Each of our balloons is 1 liter. How many of those can we fill? Okay, so what we need to do is find out how much volume will this cylinder give us at 1 atmosphere. Right. So if we have initial pressure and initial volume, oops, wrong. It's 1. And final. Right. So the initial pressure is going to be 100 atmospheres inside that cylinder. And what's the volume of the cylinder? 10 liters. Okay. The final pressure is going to be 1 atmosphere. And that's the unknown. So if we take Boyle's law and we solve for the unknown, then we have 100 times 10. This is 100 atmospheres times 10 liters, and divided by 1 liter, 1 atmosphere, excuse me. That cancels the atmospheres, and that gives us what, 1,000? Yeah, 1,000 liters at standard temperature and pressure. So with 1,000 liters, excuse me. Okay. All right. Here's the trick. With this cylinder is 10 liters. So when we take this cylinder down to 1 atmosphere, there's still going to be gas left in that cylinder. 10 liters of gas left in that cylinder. That's gas that we can't use to fill balloons. So how much gas do we have that's available to fill balloons? We have 1,000 minus 10, or 990 liters, which implies 990 balloons. Okay. If there's anybody in this group that's a scuba diver or knows a scuba diver, you know that if you're down, say, 33 feet down, that's an extra atmosphere of pressure, and your tank is depleted down to 1 atmosphere pressure, then it's not going to give you any more air. There's still air in the tank, but you can't get it because you have to inflate against another atmosphere of pressure. So that's what we're talking about here. 990 balloons is the maximum. Okay, 67. We got some time. $67. All right, I heard a ding-a-ling. Let me check. See if somebody showed up or somebody disappeared. Because if you leave before the end of the class, I have to count you absent. Arthur Dickens King. 1, 2, 3, 4, 5, 6, 7. 3, 4. Okay, we lost somebody. Okay, Ballingee's there. Kaylee's there. Yep. This is there. Wyatt. Who are we missing? Markham. Kaylee Markham disappeared on us. Okay. Just make a note. Okay. So here we have a problem with photogray lenses. Now, I think the technology has changed over the years, but originally the photograys incorporated a chemical reaction with ultraviolet light and silver chloride. When silver is precipitated by chloride in any medium, in this case, it's in the glass, in the plastic of your glass, the ultraviolet light causes the silver chloride to dissociate. And silver metal, when it's very finely divided, is black. So the stronger the light, the more silver chloride dissociates to make the lens dark. So the darkness is due to the silver that's produced as a consequence of the dissociation of silver chloride. Okay. The enthalpy of this reaction is 3.1 times 10 to the 10 squared kilojoules per mole. If we assume that all the energy supplied by light would, what is the maximum wavelength of light that can cause this reaction? Okay, so if the reaction for this process is supplied by light, right? And we know that the energy of that light is equal to Planck's constant times the frequency. Or what else can we do? Let's see. C equals lambda times frequency. So frequency equals C divided by lambda. So this could be HC divided by lambda. Okay. So what we want to do is solve this equation for a mole of molecules, kilojoules per mole. So we're looking at how many joules for each molecule, because this wavelength comes in and it's going to strike that bond, break that bond. So we want to know the energy of one of those photons. That means we need to know how much energy is required for just one molecule, right? This value here is 3.1 times 10 squared, 3.10 times 10 squared kilojoules per mole. We want to change it to joules per molecule, right? Because this value here is in joules, not kilojoules. Right? So what we have to do, remember when you're in dimensional analysis, if you've got multiple units in your starting material, then you do one at a time. So kilojoule is 1,000 joules. Right, there we go. Now we need to change molecules, moles to molecules. Right, mole goes on top because that's in the denominator, and then molecules is here. So we know that's 6.022 times 10 to the 23rd molecules. So this will tell us the amount of energy required to break one bond. Let's see, 3.10 exponent squared, 1,000 times. And then 6.022 exponent 23 divided. This is 5.148 times 10 to the minus 19th joules per molecule. Okay. So this is the energy that goes in that equation. But we want to solve it for wavelength. So let's say wavelength equals HC over E. Right, if I did my math correctly. Over here, there, yep. So what's Planck's constant? 6.626 times 10 to the minus 34 joule seconds. minus 34 joule seconds. Speed of light, 2.9979 times 10 to the 8 meters per second. And then energy is 5.148 times 10 to the minus 19th joules per molecule. We don't have to put the molecule in there now for this one. Joules cancels, seconds cancel, and we're left with meters for wavelength. Okay? 6.626 exponent 4 there, enter. 2.9979 exponent 8 times, and 5.148 exponent minus 19 divide. This is 3.86 times 10 to the minus 7 meters, or if we're going to do nanometers, a nano is 10 to the minus 9th. So if we make this 10 to the minus 9th, that moves the decimal over this way. We've made this one smaller, that one has to get bigger. That's meters. And if this is nano, then that's equal to 386 nanometers. Okay? That's an extra credit, by the way. Let's see. We got a few more minutes. Okay, 68. The calcium atom is much larger than the calcium ion. Why is that? Calcium atom is bigger than the calcium ion. That's because we've removed 2 electrons from the outermost shell, from the valence shell. And that shrinks the, that shrinks the ion in comparison to the atom. So that's true. While the fluorine atom is much smaller than the fluorine ion. That's because the fluorine ion is negative. We add an electron. Explain this natural occurrence. And I just did. The cation has a larger, while the fluorine atom is much smaller than, okay, we're actually not comparing the two. We're just saying that one ion is smaller and the other ion is bigger. Then it's neutral. So the explanation is that when you subtract electrons, you shrink it. And when you add electrons, you expand it. That's actually pretty simple. '69. Okay. I think you guys have seen this one before. ABC molecules. A has a hybridization of sp3. That's given in the table. Molecule B has 2 more effective pairs. 2 more effective pairs around the central atom than A does. And molecule C consists of sigma bond and 2 pi bonds. All right. Hybridization. And electronic geometry. Bond angle. Let's see. We'll just do this. Just like geometry class. Okay. A, B, and C. Our starting point is A with an sp3 hybridization. Then we're told, well, we know that electronic geometry is going to be tetrahedral. and its bond angles are going to be 109.5 degrees. That's given. I mean, we understand that that's what that means. Now about B. B has two more effective pairs. If it's got two more effective pairs, we've already used up all of our P's and all of our S's. The only two that we can go to now are D's. So if we have 6, 2, 3, 6, then the electronic geometry has to be octahedral. Okay. How about bond angles? Well, octahedral is going to have a square in the middle, and then it's going to have like that. So what are the possible angles? Well, if every position is occupied by an atom, then you have the possibility for 180 degrees or 90 degrees. Anywhere you look, the other one is 90 degrees. Those are the two possibilities. And then C says it has 1 sigma and 2 pi's. Remember, we have one of these and 2 of those. The only way you can have a pi bond is if you've already got a sigma. So our molecule has to be bimolecular. Can only have 2 atoms in it. One of the atoms bound to the other one, that's a sigma. We don't have any more sigmas because sigmas must be on axis. The only way you can get those other 2 pi's is to put both of them between those atoms. And that means we have a 180-degree molecule. And we also have hybridization of only that gives you a linear. That has to be sp. No other possibility. Okay, there you go. That's 69. All right. We're getting close. We're getting very close. That's the end. Okay. Are there any questions? Let's see. Let me look at the schedule. May 13th. This is the final. If you come face to face, I'll be here on that day. That's a Tuesday. If you, the schedule in the syllabus says that the final's on the 15th. This can be bright space. I'm only going to be here on that day. I won't be here on Thursday. I have to be out of town. So if you take it in bright space, you've got till the 15th. If you take it in person, I'll be here on the 13th. If nobody shows up after about 30 minutes or even less, I'll just pack up because I assume nobody's coming. But if you want to take it in bright space, send me an email so I'll know to open the exam for you. Okay, I'm going to stop the share.